So when you take a limit, you pretty much just plug in the value in for x. So here, limit x approaches a of f of x, so that's f of a. So for example, x approaches 2 for x squared, so that's just 4. And here we have 1/3. So a derivative is an instantaneous slope. It's change in y over change in x, but the change is very small. So here's a definition of a derivative, where f of x plus h is the final y minus f of x, which is the initial y, over the final x minus the initial x, and you get the definition of a derivative here. So the first rule is the power rule. You pretty much just take the exponent, put it down as a coefficient, and subtract 1 from the exponent. So x squared becomes 2x, 3x cubed becomes 9x squared, and 4 is the same as 4 times x to the 0. Take the 0, put it in the front, 0 times anything is 0. Product rule, you have f of x times g of x. So you take the derivative of the first times the second, plus the derivative of the second times the first. So for example, here we have x squared plus 1 times x plus 3. Take the derivative of the first, so you get 2x times x plus 3, and then 1 times x squared plus 1. Quotient rule is very similar, except you do derivative of the first times the second minus derivative of the second times the first divided by denominator squared. So I use the same polynomials as last time, so it's just 2x times x plus 3 minus 1 times x squared plus 1 divided by x plus 3 squared. So with the chain rule, when you have a nested function like f of g of x, you do derivative of f of g of x times the derivative of g of x. So here is a way to see how the differential of g of x cancels itself out, and you just get the derivative of f of x. So for example, f of x is x squared, g of x is 3x. Derivative of the quantity 3x squared is just a derivative using the power rule, so you bring the 2 to the front, so you get 2 times 3x, take the derivative of 3x, so that's 3. So here are some special derivatives. The trig derivative, so sine becomes cosine, cosine becomes a negative sine, tangent becomes secant squared, secant becomes secant tangent, cosecant becomes negative cosecant cotangent, cotangent becomes negative cosecant squared, natural log of x becomes 1 over x, e to the x becomes e to the x, and a to the x becomes a to the x ln of a, where a is any constant. With implicit differentiation, you use the same rules as before for normal differentiation, but when you take a derivative of y, you want to slap on a dy dx or y prime right after. For example, you have an equation 2y plus x squared is equal to y squared. So you take the derivative of y, so that's just 1. So you have 2y, but then you have to slap on a y prime, so that's 2y prime. And then you have 2x because x is normal, and then 2y y prime for y squared. So then you want to move all the y primes to one side, then you factor it out, and then you solve for y prime. So L'Hopital's rule states that when you have a limit as x approaches a number, and if f of a and g of a are both 0, or if f of a and g of a are both infinity, then that the limit of x approaches a of the derivative of f over derivative of g will be equal to the limit as x approaches a of f over g. So for example, as x approaches 0 of sine of x over x, so you know sine of x is 0 and 0 is 0, so it satisfies this rule, so you can take the derivative. So that's limit of x approaches 0 of cosine of x over 1, and cosine of 0 is 1. Applications of derivatives, so if the derivative is 0, then there's a max or min there. If the second derivative is less than 0, the function is concave down. If it's greater than 0, it's concave up. If it's 0, then there's a possible inflection point. So integration, this undoes differentiation and derivatives, and it also gives the area under a curve. So integrating from a to b of f of x dx means that you are finding the area under the curve f of x from point A to B. So the fundamental theorems of calculus states that if you take a derivative of an integral, they just cancel each other out, and you just get the function inside of the integral. And the second fundamental theorem of calculus states that if you integrate from a to b of f of x dx, then you get the antiderivative evaluated at b minus the antiderivative evaluated at a. So the reverse power rule for the integration states that if you have the integral of x to the n dx, that's just equal to x to the n plus 1 divided by n plus 1. And you have to add a constant after every indefinite integral. So for example, x squared, you just add 1 to 2, so you get x cubed over 3. So 2x, you get 2 times, so this is x to the 1, so you do x squared over 2. The 2 cancels itself out, and you just get x squared plus c. Integral of just dx, so this is the same as integral of 1 dx, which is the integral of 1 times x to the 0 dx. So you do 1 times x to the 1 over 1, which is just x plus c. So special integrals are just the same as the special derivatives, just the opposite. So sine of x dx becomes negative cosine, cosine becomes sine, 1 over x becomes ln of absolute value of x plus c, and integral of ln of x becomes x ln of x minus x plus c. So U-substitution is a good method to integrate. So you use it when you see a function and its derivative inside of the integrand. So the integrand is whatever is in between the curly s and the dx. So for example, of integral of g of x and times g prime of x dx. So you want to set u equal to g of x, then take the derivative of both sides. You get du dx is equal to g prime of x, which means that du, you multiply both sides by dx, you get du is equal to g prime of d, or g prime times dx. Substitute everything back in, and you get the integral of u du is equal to u squared over 2. So now you want to undo it. I said earlier that u was equal to g of x, so g of x squared over 2 is the answer. So here's an example where I do that. So here is tangent. I rewrote it as sine of x over cosine of x dx. So I set cosine to u, so du is equal to negative sine x, which means or dx, and then I substitute everything back in and I get the negative integral of 1 over u du, which is the same thing as negative ln of absolute value of u plus c, which is just negative natural log of cosine x plus c. So integration by parts is the reverse of the product rule. So it states, so this is using the product rule earlier, but I integrate both sides and then I rearrange it so that I'm solving for the integral of f prime g dx. So let f prime of x be 1, for example, and g of x be ln of x, and I'm trying to integrate ln of x dx, which is equal to integral of 1 times ln of x dx. And what you do is, since the derivative of f of x is 1, that means the antiderivative of it is x. And according to the formula, the first part is f times g, and g we set equal to ln of x. So the first part we get x ln of x. And we still have the second part of the integral, which is minus the integral of derivative of g times f. So since f is x and the derivative of g, which is ln of x, is 1 over x, so you have x times 1 over x, which is just 1. And 1 dx is just x. So the integral of ln of x is x ln x minus x plus c. So polar integration is similar, but x becomes theta and y becomes r, which is radius. Since in a circle the area is 1/2 theta r squared, so instead of using length times width for the area under the graph, you use that and you end up with 1/2 integrating from a to b, which is the initial theta and the final theta, of r of theta squared d theta. So the area between the curve f of x and g of x is the integral from a to b of f of x minus g of x dx. So when you rotate a volume around the x-axis, this is like creating like small disks, which are circles. So we use the formula pi r squared, so we put the pi in the front since it's a constant. Integral from a to b, and f of x is the r, so this is squared, so f of x squared dx. This gives the volume of f of x from a to b about the x-axis. So you can do the same thing, but with a hole now. So all you have to do is subtract g of x squared, and that'll give you the volume with the hole in the middle. So solving differential equations using separable equations. So this is when the dx's can be grouped with the x's and the dy's can be grouped with the y's. Then you solve by integrating both sides. So for example, here I have dy dx is equal to x squared y. So I divide both sides by y, then I integrate both sides and I get y is equal to e to the x to the third over 3 plus c. So since I can split that up to e to the c is still a constant, so it's just c e to the x cubed over 3. So solving linear ordinary differential equations, these aren't separable at all, and they are in the form of y prime plus by is equal to c. So we have to use the product rule to solve this. And so we aligned y prime with f prime, and you want to align y with f. And to make this work, you have to multiply everything by I, which is like an integrating factor. It's sort of like completing the square when you solve quadratics. You force a constant in to make it work. So here you want to make I equal to g. And notice that I is equal to, or I prime is equal to IB if you line everything up. And after you integrate both sides, or multiply both sides by this, you end up getting y prime e to the integral of b dx plus by e to the integral of b dx is equal to c e to the integral of b dx. But this is just the product rule, so we can undo this entire thing and just get y e to the integral of b dx is equal to integral of c e to the integral of b dx plus c. Now divide both sides by that integrating factor, and you get equation at the bottom that you can use to solve any equation. So for example, we have this one over here. So you divide everything by x to get y prime plus y over x is equal to 2. So we have this formula we got from the other page. So we know that c is equal to 2, b is equal to 1 over x. So now we just put everything into this equation, and it simplifies down to y is equal to x plus c. So solving second order differential equations, these aren't separable either, and they're in the form a times y prime plus b times y prime plus cy is equal to 0. So we can use e to the rx to solve this, to turn it into like a quadratic equation. So we just assume that y is equal to e to the some sort of rx. We're trying to figure out what r is. So if once you plug it in, you can see that it factors out to a quadratic. We know that e to the rx can't ever equal 0, so we just ignore it. So now we're left with a quadratic. We can use the quadratic formula to get r, and there we go. We have the general formula to get the y. So here's another example of it. 2 times y double prime plus 3y prime plus y is equal to 0. So put everything into the formula, and we get y is equal to e to the x, so that's the first solution. Then we add it to the second solution, which is e to the negative 1/2 of x.
So infinite series are just the sum of infinite numbers. So for example, the infinite series from 1 to infinity of n means that it's just 1 plus 2 plus 3 plus 4 plus 5 all the way to infinity. A series either converges or diverges. Diverges means that the sum is either negative infinity, or if the sum never settles down to a constant. Converges means that a sum approaches a constant. So you have to apply different tests to test for divergence or convergence. So the nth term test is the first one. So what you want to do is plug in infinity for n into a of n, which is your series. And if it's infinity or a constant, that means it diverges. If it's 0, it is inconclusive. So for example, the series from 1 to infinity of n, since you plug in n for infinity, a of n also goes to infinity, which means it diverges. Here you have the series from 1 to infinity of 1 over n, and since when you plug in infinity for n, a of n goes to 0, which means the test is inconclusive. So here are some special series. Here's the 1 over n again. It's a special series that diverges using the integral test I'll show later. And P series, which is the integral from 1 to infinity of 1 over n to any power. And if P is less than or equal to 1, the series diverges. And if it is greater than 1, it converges. So a geometric series is this, where you have the sum from 0 to infinity of a, r to the n, where a is the initial value, r is the common ratio. If r, with the common ratio, is less than 1 and greater than -1, it converges to a over 1 minus r. So for example, a series of 0 to infinity of 1/2 n, so that converges to 1 over 1 minus 1/2. So the integral test, you want to substitute x in for all the n's in the sum, the series. And so for example, 1 over n becomes 1 over x, n squared becomes x squared. So if this new x, this f of x, is continuous, positive, and decreasing, that means the integral test works. So that fits perfectly with the 1 over n. So I convert it to the integral of 1 to infinity of 1 over x dx, which becomes ln of x evaluated from 1 to infinity. And that's just ln of infinity, which is just infinity, minus ln of 0, which is 1, which is still infinity, which means this thing diverges. Compare that to a 1 to infinity series of 1 over n squared. You do the integral test and you get 1 to infinity of x squared dx. And that's the same thing as negative 1 over x from 1 to infinity, which is just -1. Since -1 is a constant, that means the series converges. But note that 1 isn't the sum, but since -1 is a constant, it still converges. So the comparison test is if a of n is less than b of n, and b of n converges, a of n also does. If a of n is greater than b of n, then the test is inconclusive. And so, for example, I have 1 over n squared. We know that this thing converges, so we set that as the b of n. And we have this other function as a of n of 1 over n squared plus n plus 7. Since a is less than bn for all n's, and bn converges, an also converges. So limit comparison test is also useful when the comparison test doesn't work. So it's pretty much saying is limit as n approaches infinity of an over bn and is equal to a constant, both an and bn converge or they both diverge. So the same thing as last time, set bn to 1 over n squared since you know it converges. Set an to the what you want to solve for, which this time is 1 over n squared minus n minus 7. But since a of n is greater than b of n for all n's, that means comparison test won't work. We can use limit comparison test to solve for it. So here I show that it comes out to 1. And since 1 is a constant and b of n converges, a of n also converges. So if a limit as n approaches infinity of a of n plus 1 divided by a of n is less than 1, that means it converges. If it's greater than 1, it diverges. If it is equal to 1, it is inconclusive. And so if, for example, from 0 to infinity of 2n over n factorial, so here we take the limit of n approaches infinity, so you add 1 to the n, so it's 2n plus 1 over n plus 1 factorial over 2 of n over n factorial, which is the original function. So you take the reciprocal, the keep change flip from 5th grade, and you cancel everything out. You end up with limit as n approaches infinity of 2 over n plus 1, which is just 0. Since 0 is less than 1, the series converges. So root test is very similar.
except you use a root instead, where n approaches infinity of the nth root of a of n. If it's less than 1, series converges, greater than 1, diverges, equal to 1 is inconclusive. So for example, if you have the series from 1 to infinity of 3 of n, 3 to the n to the times n to the n divided by 2 to the n, that's the same thing as saying 1 to infinity of 3n over 2, that entire thing to the n power. So that is the a of n, so you take the nth root of that, so then these two n's cancel out, which leaves you with the limit as n approaches infinity of 3n over 2, which is infinity, and since infinity is greater than 1, the series diverges. So alternating series test is one of the easier ones, where if you have a series that has a -1 to the n plus k, where k is any constant, usually it's just 0 or 1. And so if the remaining part of the series approaches 0 as n approaches infinity, then the series converges. So for example, a series from 1 to infinity of 1 over n times -1 to the n. So you want to just ignore the -1 to the n part and just think about 1 over n. When you plug infinity into it, so as that means that 1 over n approaches 0 when n approaches infinity, and since that happens, the series converges. So Maclaurin series are used to approximate non-polynomial functions such as e to the x, ln of x, sine of x, cosine of x, and using polynomials. So what you do is Maclaurin series of x is equal to f of 0, which is what you're trying to approximate, plus f prime of 0 of x times x plus the second derivative of 0, x squared over 2. So following this pattern is just the nth derivative evaluated at 0 of the function you're trying to approximate times x to the n power divided by n factorial. So for example, we do this with e, so e to the x is equal to e to the 0, which is 1, plus e to the 0 times x plus e to the 0 x squared divided by 2, all the way up to e to the 0 times x to the n over n factorial. So we can rewrite this as a series. So it's series from 0 to infinity of x to the n over n factorial. So Taylor's series centered at the point x is equal to c of x is equal to f of c plus the derivative evaluated at c times x minus c, plus the second derivative evaluated at c times x minus c squared over 2, plus this derivative, the nth derivative evaluated at c times x minus c to the n over n factorial, where c is the center of approximation of the curve. So the alternating series remainder, this is an estimate for convergent alternating series, like to get like an actual value from it. So what you want to do is, if you want to estimate like the fifth term here, for example, then you put the first 5 terms in, and what you do is you use the 6th term to find the error. So if you see here that the 6th term here would be plus 1 over 6, the 7th term will be minus 1 over 7, and everything beyond that will be smaller than 1 over 6. So we're subtracting something that's smaller than 1 over 6 from 1 over 6, leaving us with something that is less than 1 over 6. And this number is also greater than 0, so we know that the remainder is between 0 and 1 over 6. So then we know that the sum is just -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 with an error of 0.7. So Taylor's remainder theorem is pretty similar to this, but it's used to measure the accuracy of a Taylor's expansion series. So this is the formula you have to use, where m here is the bound on the nth derivative of the original function, and c is the center. So here's like a practice question. To estimate the error for sine of 0.7 from its Taylor series with degree 3. So degree is n, so we plug n in for 3. And notice how sine always goes between 0 and 1. And like the derivative of it is cosine, which does the same thing. So you know that the nth derivative of f of x, which is sine of x, will always be less than or equal to 1. So we can set m equal to 1. So e of x is equal to 1 times, so x here would be 0.7 minus 0, since we're centered at 0, to the power of 3 plus 1, since we're doing the third degree, and then over the 3 plus 1 factorial. So we get 0.7 to the 4th power over 24. 24 is just 4 factorial, and you get about 0.1 error.